Hello, everyone, and welcome to the 52nd session of the Post-Media Tea Time Talks. I am Ramin with my wonderful colleague Sarah and the two great presenters today. We are very happy actually that we have had really a lot of good speakers this year. And this is the last session actually before going on to Christmas holiday. So we are extra excited about that as well. So the first speaker is Philip Salter, who is a PhD researcher in the Department of Civil and Environmental Engineering at the University of Strathclyde in the UK. He has a bachelor degree in combined science, technology and engineering and mathematics from the Open University. And right now he's a part of a PhD program at the GeoNetZero program, where he does experiments to study different ways that we can engineer the subsurface to optimize renewable technologies and accelerate the decarbonization of our society. And today he's going to talk about induced carbonate precipitation to enhance and improve reservoir storage integrity and geothermal system efficiency. So without further ado, the floor is yours. And Philip, it's a great pleasure to have you here today. So please go ahead, and we are very much looking forward to listening to your talk and learning more about your work.
Thanks very much, Ramin.
Yes.
Okay, can you see my screen?
Yes.
Okay. So yes, my name is Philip Salter and I'm a PhD researcher at the University of Strathclyde in Glasgow. And today I'm excited to present to you some of my research and the potential of induced carbonate precipitation for improving CO2 storage integrity. Legacy oil and gas wells are often cited as the greatest risk for leakage of geosequestered CO2. There can be gapping at the casing host rock interface, existing faults and fractures, cracks in wellbore cement, and shrinkage of cement, all of which can act as leakage pathways back to the surface. In addition, if we are to repurpose oil and gas infrastructure for CO2 injection, there can be unconsolidated and high permeability regions around the well, which reduce sweep efficiency, that is the lateral migration of CO2. The aim of this project is to design a toolbox of solutions using induced carbonate precipitation to remediate oil and gas wells. So what is induced carbonate precipitation? Well, it mimics a naturally occurring crystallization process caused by soil bacteria that produce the enzyme urease. We can either inject the bacteria directly, as shown in this video on the right, produced by Abdel Data. We can extract the enzyme from the bacteria or from plant-based sources such as soybeans and jack beans. On injection of a solution of urea and a calcium source, typically calcium chloride, the urea is broken down by the urease enzyme, releasing carbonate ions into solution, which can then react with calcium to form calcium carbonate. This has been investigated for several applications, including the prevention of coastal erosion and soil stabilization, sustainable construction materials, modifying the thermal properties of soil and rock, and for permeability reduction and improving CO2 storage integrity, which I'll focus on today. So in our initial set of experiments, we extracted the urease enzyme from jack beans. The idea behind using the enzyme instead of the bacteria is that it is much smaller, typically around 9 nanometers, whereas the bacteria is around half a micron in diameter and several micron in length. So we injected this solution of enzyme while simultaneously injecting a solution of urea and calcium chloride, and allowed the two solutions to mix within porous media. While this was happening, we captured high-resolution XCT images to capture the dynamics of the crystallization process. One scan was captured pre-enzyme-induced carbonate precipitation, and then 10 scans during it with a reconstructed voxel size of around 8 micrometer. So on the left, you see the quartz sand prior to the reaction, and then on the right, after a 1 hour precipitation period. The results of this initial study were that precipitation occurred mainly across the mixing profile of the two fluids, and as shown by this blue to red region here, here the crystals are colored by their volume, with blue signifying the smaller crystals and red the larger ones. And we can also assign values to crystals based on their effect on local flow velocity, as well as their proximity to the grain contact points. By running flow simulations across both the full volume and also across these smaller subvolumes, we can see the effect on permeability as the crystals form. And what we find is that in this red subvolume, we have up to a 37% reduction in simulated permeability over a 1 hour period. But outside of this main precipitation band, we have a much lower reduction in permeability. And there was no obvious relationship between where the crystals formed and the sand contact points. So what can we do to better control where and when these crystals form? Well, several single-phase injection strategies have been proposed, which allow us to mix the urease, either from bacteria or plant-based sources, with the urea and calcium chloride, and create a lag period that prevents crystals forming initially. So the first of these is soybean enzyme-induced carbonate precipitation, where we take advantage of the naturally lower pH of soybeans, which delays the crystallization reaction by 2 to 4 hours. The second is low pH microbially induced carbonate precipitation, which follows a similar mechanism, but requires an additional acid. Typically, we use acetic acid due to its high buffer capacity, which also delays the onset of crystallization, and firmly delayed EICP using agricultural urease inhibitors. So the idea here is that the urease inhibitor attaches itself to the urease enzyme and prevents it from breaking down urea. But this only works up to around 35 degrees centigrade, so we can inject a cold single-phase solution into the rock, and due to the higher temperature in the subsurface, the urease inhibitor breaks down and allows the crystallization reaction to happen. So if we take the first of those single-phase injection strategies, the soybean EICP, we see that calcium carbonate forms initially at grain contact points, driven by the coagulation and dropout of other proteins in solution, which then act as primary nucleation sites for crystal growth. And then, as we might expect, the crystals that form during later cycles, they form on the calcite that was formed during the earlier injection cycles. And due to this, we see a high increase in strength with solidification of sand in just 2 to 3 single-phase cycles at a low volumetric percentage of calcite. So here are 3 larger samples prepared using that method. As you can see on the left, after 3 cycles, we already have quite a high degree of solidification. One of the other tests we performed on these samples was a falling head permeability test. And what we found is that several cycles were required for a large reduction in permeability. And this was despite a large increase in compressional strength. This has important implications on sustainable ground engineering, where it may be beneficial to retain permeability, for instance, in applications such as coastal erosion and soil stabilization. We also conducted UCS tests for these samples, After 3 cycles, the UCS was 2.3 megapascal at 6.7% calcium carbonate. After 6 cycles, this was up to 5.2 MPa. And after 9 cycles, the machine went up to its maximal load of 25,000 newtons and failed to break the samples. So we now need either smaller samples or a more powerful machine, basically. So we know that this process works in highly uniform quartz sand, but what about in polymineralic and heterogeneous systems more representative of real rocks? So what you see here is a granitic sand with a fine layer of sand separating 2 coarser layers. The fine sand had a typical grain size diameter of less than 100 micron. Next to that, you see the sample after 3 cycles of soybean enzyme-induced carbonate precipitation. And what we found is that calcite forms both across this fine layer and on the other side of it. By running flow simulations before and after these crystals form, and subtracting the velocity field of the later time point from the earlier one, we can begin to see the effect that these crystals are having on local flow velocity. So here, the crystals are colored from blue to red, with blue indicating a reduction in flow velocity and red an increase. And what we find is that the crystals that form within the fine layer show a reduction in flow velocity, whereas the crystals outside of it have a more complex effect. And if we look at that larger sample, we see that it is an increase in tortuosity caused by the precipitation in this fine layer that is reducing permeability. And other studies have found that small changes in capillary entry pressure, contrast, are sufficient to divert the flow of CO2. So what that means is we're effectively reducing the vertical to horizontal permeability ratio, which should, in theory, help spread out the flow of CO2, improving sweep and storage efficiency. So how does that compare to single-phase microbially induced carbonate precipitation? Well, again, on the top, we have the soybean process, and we see that crystals are forming both within the fine layer and on the other side of it. If we plot the mean vertical distribution of this calcium carbonate precipitation, we see that the crystals are forming mostly across this fine layer. In contrast, the microbially induced precipitation, we saw lots of crystals forming in this inlet region, but much fewer reaching the fine layer and even fewer breaching through to the other side of it. The low pH microbially induced carbonate precipitation process, the buffer capacity of the solution is influenced by the cell density, the pH, and the ureolytic activity of the bacteria. So it's quite hard to control when compared to the soybean process. And what we think happened here is that a bacteria flocculated within this inlet region, causing a more localized permeability reduction, which actually may be useful for reducing permeability in the immediate vicinity of legacy oil and gas wells, leaky legacy oil and gas wells. So what are the conclusions of our studies so far? Well, using soybean urease allows precipitation across fine sand, and this may increase sweep efficiency by reducing the vertical to horizontal permeability ratio. Microbial strategies may work better for targeted near wellbore permeability reduction, preventing CO2 leakage from legacy wells. And understanding where and how these crystals form will inform larger scale models. Our future sets of experiments at this Diamond Light Source synchrotron facility will investigate thermally delayed strategies that could be crucial in controlling the onset precipitation. And we'll also look at dissolution of this precipitated calcium carbonate by CO2-enriched brine. So what some of you may be interested in is could this be a way of making lower carbon construction materials? Well, it is complicated because the reagents that we use typically have a high carbon footprint. but I think it is possible if you were to induce elements of circularity within the process using various waste streams to resynthesize our primary reagents. And the other case study, which unfortunately I've not been able to talk about too much today, is geothermal and thermal energy storage. And what we've found so far is that precipitated calcium carbonate can increase the thermal conductivity of dry quartz sand by around 470% after 9 treatment cycles. The addition of conductive additives, the one we've found most beneficial is expanded natural graphite, can enhance this effect even further. By up to 800% increase in thermal conductivity at 5 weight%. We can also absorb phase change materials such as paraffin into the expanded graphite, increasing its thermal energy storage potential by increasing the latent heat across this phase change. Our future work will investigate surface percolation of graphite EIC suspensions, potentially for use around high voltage electrical wires, which are prone to overheating, and ground source heat pumps, which could be used both for cooling and for heating in winter. So I'd like to thank the organizers for inviting me to speak today, and my supervisors, Kate Dobson and James Minto, for their support during my project. Thank you.
Thank you very much, Philippe, for this really nice talk. So you showed really a bunch of interesting results, and with also challenging applications, so that's really cool for you, and thanks for this. So first, if there is any question from the audience, please feel free to write them in the comments, and we will ask them to our speakers. Maybe I will start with one of my own. You mentioned that for microbially induced precipitation, you don't see preferential patterns in the crystal growth areas, right? Whereas in the context of soy-boy urea precipitation, you observe this. So I would like to understand the difference between both of them, and why in one case you have preferential areas of growing crystal calcite instead of the other one.
So these results are actually quite in line with what we've seen in other studies. Typically when the grain size is very small like that, so less than 100 micron, the bacteria are unable to get across that layer just due to their physically bigger size. They kind of get filtered out by that fine layer of sand. So that's why we think we saw lots of crystals forming before the fine layer, but not many on the other side of it.
Okay, and do you see any patterns linked with the geometry of the sample? For instance, like preferential area directly related to a proportion of aggregates, crystal aggregates around the matrix, the soil matrix.
So during the soybean process, there doesn't seem to be much effect of grain size or shape distribution or mineralogy. It doesn't seem to be as affected as the bacteria. So what we might find with bacteria is that certain charged minerals. So in some of our samples, we have pieces of mica, which are quite highly charged, which the bacteria may either be attracted to or repelled by. It doesn't seem to affect the soybean EICP process in the same way.
Okay, thank you. So in the meantime, we had a question from the audience, from Syed Salab. So he's asking, what is the relationship between the treatment cycles and the calcite mass content?
So it depends on the treatment strategy you're using, but the more treatment cycles, the more calcite you will have effectively. And I spoke a little bit about this chemicals urea and calcium chloride that we use. Typically, there's an upper limit of how much you can inject at any one time. If you go past that point, you get diminishing efficiency of how those reactants are used. Which is obviously not a good thing if you're trying to keep the costs down of your treatment cycles. You want all the urea to be broken down and all the calcium chloride to be used. So we find during the soybean process is very, very efficient, up to, so we use 1 molar equimolar solution of urea and calcium chloride, and at this level 95% of the reactants are being used up during the reaction.
So he's having a reaction to your answer. So for example, the results for the increase in thermal conductivity, this 9 cycle, correspond to how much calcite?
Yeah, so after 9 cycles, we're typically up at around kind of 15 to 20% by mass calcite.
Okay, thank you. And I will have like a rather environmental question on this question of repeating cycles, actually, because you mentioned you're using acetic acid, right?
Yeah.
So if you want to reduce very much the permeability, you will have to provide several cycles. And what would be the impact of this process on like the global microbiological environment?
As of the addition of the acetic acid in the microbial.
Yeah.
So I don't know the impact of that on other microbes. I think it's a fairly mild, it's a weak acid. So, and effectively what happens as the reaction happens, the pH will go up. We see a trend. So if we're starting around pH 4.5, for instance, this set of experiments, we reduced the pH to about 4.5 using acetic acid. But as the reaction progresses, we end up at a much more neutral pH. It's more like between 7 and 8. So those acids are neutralized by the reaction occurring.
Okay, thank you.
Thanks.
So do we have any other question from the studio or from the audience?
No, I don't have any questions. Yes, it was very interesting to learn how basically nature can do a lot for us. I mean, in terms of all the processes that we always looking for something chemical or man-made, but things are in nature actually that we can use. Really interested talk, and thank you very much, Philip, again.
Well, thank you again for inviting me. Thanks.
Yeah. So thanks again, Philippe, and I think we can move to our second speakers of the day, which is Giulia Ceriotti, which is trained as an environmental engineering. She was awarded with a PhD at the Politecnico di Milano in Italy, with a thesis on modeling reactive transports in porous media under uncertainty. And during her postdoctoral experience at the University of Sydney in Australia and the University of Lausanne in Switzerland, she developed her research at the interface between fluid mechanics and biogeochemistry, using novel experimental microfluidic approaches to study microbial-mediated oxygen cycling at the pore-scale in soil and aquifers. So currently, our research focuses on developing interdisciplinary experimental methods to understand and control bacterial response to pore-scale biogeochemical heterogeneities and its relapse on microscopic contaminant degradation in natural and engineering systems. And today she is presenting how pore-scale oxygen distribution impacts large-scale biogeochemical processes in aquifers. So, Giulia, thanks again for accepting our invitation, and the floor is yours.
Thank you very much for the introduction. Thank you for inviting me. So I will share my screen now so you can see the presentation. Can you see?
Yes, we see your presentation.
Okay. So as Sarah correctly said, my research focus on biogeochemical processes in complex natural structures, porous structures, which include, of course, aquifer, but also soils, the rhizosphere, lake sediment, marine sediment. So as you might already know, subsurface system populated by a huge number of bacteria that are hugely diversified, and this makes the biogeochemistry of this environment extremely complex. One of the most important drivers of microbial activity in the subsurface is oxygen content. Oxygen is supplied to the subsurface from the atmosphere. So what we generally expect to see is that oxygen concentration decrease with that. And this means that the respiration of bacteria somehow respond to this oxygen concentration. So in shallow oxic layer, like soils or shallow aquifer, bacteria are expected to respire aerobically. So it means that they take oxygen as electron acceptor, which is the most favorable one. However, when oxygen disappears, so in deeper anoxic layer, bacteria are very flexible metabolism, so they can switch to alternative respiration style, which are called anaerobic respiration. And anaerobic respiration is much more diversified than aerobic one. So, for example, bacteria can use nitrates, uranium, chromium as electron acceptor to gain energy. And if someone is familiar with this type of compounds, you might notice that are very important contaminant in the environment. So anaerobic respiration is known, for example, to help remediating subsurface system. Sometimes instead they contribute to, the anaerobic respiration contributes to pollution instead. So they're producing as byproduct, for example, greenhouse gases. So the key point here is that anaerobic respiration is often easy detectable because it has a clear signature in terms of electron acceptor uptaken and bioproducts produced. Recent evidence in the environment have shown that, surprisingly, anaerobic respiration takes place also in shallow oxic layers. Why is that possible? So we assume always that bacteria prefer to expire oxygen. So why they should expire something else when oxygen is available? So the most accepted hypothesis is that our characterization of the shallow layers is based on bulk measurements of oxygen. So we can only characterize the average content of oxygen in our system. So for us, the system is oxic. But if we imagine to zoom in at the microscale, so sub-millimeter scale, what we should expect to see is a very heterogeneous environment with a heterogeneous distribution of oxygen and the formation of these localized oxygen depleted zones that are called anoxic microsite. Anoxic microsite are estimated to occupy a very tiny portion of pore space, so below the 10%, and that's why we cannot see them with bulk measurements. And they are formed by a complex coupling between pore water flow, solute transport, and microbial activity. In particular, aerobic respiration, that is uptaking oxygen in specific location where bacterial colonies are formed. So since we have this anoxic condition happening even in bulk oxygenated system, anaerobic respiration can potentially be hosted also in oxic environment. So far, we don't know much about anoxic microsite formation. It's very difficult from methodological point of view to observe them, to monitor them in the field. This is, and also in the laboratory, it's quite complex, mostly because microbial ecology, the traditional approach of microbial ecology is the use of batch incubation. So batch incubation are well-mixed reactor where we can measure in time the evolution of byproducts or microbial growth. But as you can imagine, since they're well-mixed, we cannot get any information on the spatial organization of bacteria, and we're actually dissipating all the gradients, microscale gradients. Recent advancements in technology, however, are helping us to set up new approaches. One of the most commonly used now is microfluidics device. So microfluidics devices are very tiny chip that we can etch with any desired geometry. So for example, we can replicate the structure of sands, grains, soils, whatever we like. And these are fully transparent and they can be placed on the microscope. This means that I can observe what's happening inside my pore structure in real time and in a non-invasive way. And I can replicate my system as many times as I want. So microfluidics devices are now used a lot to study biophysical processes. So for example, how bacteria organize in space, or how they respond to impulse gradient, or how they move in space. However, what we still miss now is the geochemical characterization of the system. So for example, how pH is distributed in space, or how oxygen is distributed in space. So what I'm doing with my research is developing this new type of microfluidics device that I call sensing microfluidics device that integrates geochemical approaches into this microfluidics device. So today I will show you an application with an oxygen planar sensor that is a fully transparent sensor. It's dynamic, so I can see how oxygen change in space and time without touching or being invasive in my system. To give you a more clear idea what I mean of oxygen mapping, I'm showing here the very first application that I did. It's my very first experiment with oxygen sensor. I was injecting two solutions in a porous structure. One is fully oxic, the other one is chemically anoxic. And I could detect in real time the formation of these super tiny gradients, micro-scale gradient of oxygen at the interface of these two solutions. So using this approach, what we wanted to do is to replicate in the laboratory the formation of an oxic microsite driven by aerobic respiration. So we designed a microfluidics device that is replicating the structure of sand, and we integrated it with an oxygen planar sensor. You see this chip is 26 millimeter long, so it fits perfectly on a glass slide for microscope, and it can be attached to a syringe and a syringe pump that is setting up the pore water flow into my system. So before starting the flow, I inoculated the chip with an aerobic strain called Pseudomonas putida GB1. This strain is aerobic, and it will be my model strain in this experiment. Then the syringe is filled up with a nutrient solution and an oxygen-rich solution. So I'm providing to my bacteria continuously nutrients and oxygen. And every hour I map on the entire chip landscape biomass organization, which means how bacteria are organized in space, and oxygen concentration. The entire experiment lasted for 45 hours, and based on the flow rate that I imposed, the entire experiment lasted more or less 80 pore volume times. So the type of maps that I get every hour looks like this. So here you see this is the biomass distribution. You can see these green dots are bacterial clusters, colony, and this is the concentration of oxygen distributed in space. So you can see I have this map that it's covering the entire 26 millimeter of my pore space. So it means that if I one step back from the map, I can still characterize the system through a traditional way, so according to bulk quantities. So if I look at the bulk oxygen, which means essentially the average concentration of oxygen in this map, I can see that my system stays fully oxid for the entire duration of the experiment. The biomass has a typical logistic shape, so we have an exponential growth phase followed by a stationary phase, which is exactly what we expect when we have aerobic bacteria growing in a chip. But we can clearly see that the oxygen is not distributed homogeneously in the chip. We have these red dots that are anoxic microsite. So thanks to our maps, we can identify which part of the pore space is characterized by low concentration of oxygen, so anoxic microsite. We define a threshold, a criterion. So we use as a criterion 80% of the bulk oxygen. Everything is below this threshold for us is considered anoxic microsite. So for people that are familiar with the concept of anoxia in environment, this is clearly not an anoxic threshold. We are still kind of in the oxic condition, but the idea is that we want to identify points that were characterized by a different oxygen concentration compared to the bulk, significantly lower, which potentially can trigger some anaerobic processes. For example, denitrification is known to be triggered also a quite high concentration of oxygen. Even though I use this quite mild threshold, the total amount of anoxic microsite that I see in my space, it's around 1–2% of the pore space. So it's clearly a minority of the entire pore space. So overall, this type of approach that we used is capturing the silent feature of what was postulated in the environment. So we have a fully oxic system that still can sustain some pore-scale heterogeneous distribution of oxygen, and where anoxic microsite cannot be detected by bulk measurements because they occupy just a minority of the pore space. So one thing that I skipped before is that these maps are covering the entire landscape. So we have 26mm long maps, but they're also high resolution maps because they are collected by stitching together many different pictures, high resolution picture. So our resolution is around 1.1 micron per pixel. And here I present the two zoom in into the chip, one located at the center of the chip, one close to the outlet, just to show you what's happening at the level of the colony scale, at the bacteria cluster scale. So here you have the biomass evolution in time, and here the oxygen distribution. And you can see that we are starting for a very similar initial condition in the two locations, but the morphology of the colony that we get at the end is very different. So here in the center of the chip, we have this very rounded, dense cluster, while at the outlet of my chip, I have this more elongated structure, filamentous structure. And somehow this is reflecting on the oxygen concentration that we observe. So the rounded colony can support the formation of an anoxic microsite, while we don't affect oxygen concentration if we just have a filamentous colony. So we got very curious about this morphology impact, and we try to investigate more this aspect. So we try to understand what's the physical process behind. So if we think about the formation of an anoxic microsite, we have to imagine that we have two competing processes. We have oxygen demand, so aerobic respiration uptake by bacteria that are growing, and the oxygen demand scales with the area of the colony. The bigger is the colony, the more bacteria I have there, the more they consume oxygen. On the other hand, we also have oxygen supply. So we have a physical process that is providing oxygen to my colony. And this process is diffusion. So from the colony surface, oxygen diffusing from the bulk to the colony core. In this case, we can, of course, consider area as a driving factor, because the larger is the colony area, the more surface of exchange we have between the bulk and the colony. But we can also see how the morphology can impact the diffusion process. So if we define lambda, the diffusion landscape, we can see that in rounded colony, lambda is much higher than in elongated colony. So this should slow down the diffusion process. So we define this diffusion landscape as a colony shape factor, and we define it as 2 times the area of the colony divided by the perimeter, which means that if the colony is rounded, lambda tend to be maximized and equivalent to the equivalent radius of the colony. Instead, when we have elongated colonies, lambda tends to be much smaller than the equivalent radius, which speed up the supply of oxygen to the colony core. So to see if our model was working and interpreting what's happening in our system, we prepared this plot where we have the prediction on the x-axis and the result, the reality in our y-axis. So on the x-axis, we have Damköhler number, which is we define as the ratio between the oxygen demand of each colony and the oxygen supply. So if the Damköhler number is larger than 1, it means that oxygen demand is much, much more important than oxygen supply. So we should expect the formation of an anoxic microsite. Instead, if Damköhler is lower than 1, it means that the oxygen supplied by diffusion is more important, it's faster, this process is faster, so the colony should remain oxic. So on the y-axis, we have the real oxygen that we measure inside our colonies, because we have the oxygen map. So we can characterize each colony with its own oxygen concentration. And if I plot all the colonies that we observed in our system, you can see that indeed our interpretation is quite correct. So when we have a lot of colonies that are clustering here that probably are not big enough or elongated, so they stay oxic. But in some cases, the oxygen demand is so intense that we can see the formation of an oxic microsite. So this means that the morphology of the colony is a driving factor for anoxic microsite formation and should be accounted for when we imagine to predict anoxic microsite formation in real system. So far, I just talked about how anoxic microsites are formed, but I opened my presentation with quite a big statement saying that these anoxic microsites can host anaerobic processes and can drive macroscopic environmental phenomena like contaminant degradation of greenhouse gas emission. So in these slides, I will show you some preliminary results that I'm collecting right now, but I'm really excited about, so I want to share them, where I'm using exactly the same setup as before. So we have this microfluidics device integrated with an oxygen sensor. Well, with some modification. So instead of using an anaerobic strain, I'm using this new strain that it's called Pseudomonas veroni, which is a facultative anaerobe. This means that when oxygen is present, veroni perform aerobic respiration. However, when oxygen is no longer present, Pseudomonas veroni has a flexible lifestyle, so it can switch to the use of nitrates as a source of energy and can still thrive. This is producing molecular nitrogen. And for those that are familiar with nitrates, you might guess that this is an important bioremediation process. So we are uptaking nitrates that are very spread contaminant in the environment, and we are releasing an inert compound that is just molecular nitrogen. So of course, since Pseudomonas veroni can use nitrates as electron acceptor, we had to add some nitrates to our input, so to the inflow, just to allow veroni to use nitrate when he wants to. The rest of the experiment is very similar to what I've done before. So every hour I map biomass and oxygen, and you can see that the behavior is not that different from what we saw before. So we have this cluster of bacteria, and when they're big enough and rounded, they can support the depletion of oxygen. And the entire experiment duration lasted a little bit longer than before. We set up a higher flow rate also. So overall, we have more or less 200 per volume time. So if we investigate the system in terms of total amount of pore space occupied by anoxic microsite, as we did before, you can see that we have a very similar behavior. So we have 0 at the beginning, then the colonies start forming, and we start seeing the formation of anoxic microsite with a peak around 0.7% of the pore space. So we are talking really about a minority of the pore space. And then during the stationary phase, we are stable around 0.3, 0.4% of the pore space. So how do I see if this anoxic microsite can really lead to macroscopic impact? I did an extra modification to my system. So instead of wasting the outflow of my chip, I'm starting collecting it in different moments of the experiment with a very dedicated collector system. And I developed a system to measure nitrates in tiny volume that are discharged by microfluidics device. So we are talking about 30 microliter per hour, which means that we not apply the typical analytical techniques for nitrates. So I use a special spectrophotometric measurements, and I could see that in time, nitrates decrease in the outflow. So the breakthrough curve is not complete yet, but you can clearly see that something is happening, and almost 60% of the nitrates are gone after at the end of the experiment. So what we are guessing is that Pseudomonas veroni is actually using nitrates and removing nitrates from our flow. How can I be sure that it's anaerobic respiration and it's just not some abiotic factor? So what I did, I ran the experiment again with a genetically modified Pseudomonas veroni. So what we asked our fundamental biology department to modify the genome of veroni and to knock out the gene that it's enable Pseudomonas veroni to perform the nitrification. So Pseudomonas veroni can still grow aerobically, but it cannot uptake nitrates. And what you can see is that if I use this strain, nitrate stays the same as the inlet. So it really means that it's when the anaerobic respiration of veroni is triggered we can see removal of nitrates. So just to conclude, and I hope I convince you that microscale biogeochemistry is relevant, even though it's occupying a minority, it's characterizing a minority of the pore space, it's really important to account for it in modeling and in large-scale modeling, because it can go to outside impact in porous structures. So far, it's still poorly understood, but the techniques in in-situ microscale biogeochemistry are advancing very fast. So I include my sensing microfluidics in these new technologies. And indeed, just to give you an idea how flexible and how interesting the techniques are, we are also applying them to other type of bacteria, other type of system that include mineral and microbial interaction, where we are studying how iron reduction is driven by bacteria in fully oxy system. And we're also studying how soil microbial community is interacting with roots in a microfluidics device where we are growing a real plant. With this, I conclude my talk, and I thank all my fundings and collaborators that are supporting this work. And thank you very much for your attention.
Thank you very much, Giulia, once again. It was a very interesting talk. I fully appreciate actually the fact that we always need to go to the Pore-scale to basically understand the physics behind a lot of larger scale processes. So I have just two questions from my side before actually taking the questions from the comments or from Sarah. So one question towards the setup that I was not really able to grasp during your talk. So you do this kind of test in a fully saturated condition, or is it
fully saturated? Yeah.
Okay, so how are you planning actually to do maybe partially saturated porous media as well?
It's possible, definitely. I ran some tests. The problem with partially saturated system is that the amount of pore space occupied by gas and water is not fully controllable. So every time you run the experiment again, you might end up with a different saturation index. But it's very interesting, and I expect to have very different results, to be honest. So what's happening in the soil, indeed, that it's almost always unsaturated. There are two important phenomena that I expect to see. One, it's a different distribution of bacteria, because bacteria, when they get trapped on bubble surface, they get stuck there. So it's very difficult for them to move or swim away from bubbles. So it might be possible that clustering is regulated by different physical processes there. And also bubbles are essentially a huge source of oxygen, where diffusion is much faster than in fluids. So it might be possible that it's harder to get anoxic microcyte formation in unsaturated system. However, I can already tell you that, for example, in the plant on a chip setup, you can still see there is a bubble here indeed, and the bubble here. This is saturated instead. And we can still see anoxic microcyte formation because the root is uptaking a lot of oxygen. So in the soils, they're the most common unsaturated system I'm interested in. We should also consider the interaction between the root and the soil community.
Yes, very interesting, and I understand it gets very much complicated to include all these parameters. So one more just basic question. So this, you mentioned this diffusion, which we can suppose it's based on the Fick's law from the high concentration to the low concentration. But have you tried, or are you planning to basically measure the diffusion rates? Because what I can assume is that over time we will have an equilibrium. So these microcytes, I mean, I'm talking about like really large time scales. Can we expect these microcytes to basically disappear over time when we have an equilibrium state?
So the evidence from field investigation is that anoxic microcytes are not ever reaching a stationary phase. So they kind of switch on and switch off in time. So if you perform a very long experiment, I did a test also again on much longer time. And I did see this. So the colonies are creating anoxic microcyte. When the situation becomes a little bit stressful for the bacteria, they reduce a lot their uptake of oxygen, or they switch to anaerobic respiration. So it's really hard to find a bacterium that is strictly aerobic. So they always can perform some kind of fermentative stationary phase, so stationary respiration. So the microbial response is very complex. So what I expect to see in a long-term run is that this kind of hotspot that are switching on and switched off continuously. And then maybe they change the location and first switched on in one point and then switch on in another point.
I see.
So that's another important aspect of why it's so difficult to measure an optic microsighting field.
Yes.
Because it's not just the spatial scale, it's also the temporal scale. They last for hours and then they disappear and then they appear again.
So it's in both intermittent and also the diffusion rates are extremely low. So it's because I was worried about those bacteria at the boundary, because those are at the middle, so they have more basic chance to survive.
For sure, we have a direction of the flow, right? So the carbon source in this case is coming from a specific direction. So of course, the bacteria that are located closer to the inlet are favored. So they have more oxygen, more carbon available. So this is a huge simplification compared to reality. If you think about soil or aquifer, the supply of organic carbon, it's often intermittent or not. It's not DOC, so it's not dissolved organic carbon, but it's more particulate. So it could be interesting to actually replace the carbon source with a different type, some particulate that are like located inside the porous media, simulating the aggregates of soils or aquifer. And in that case, it's just a matter of who is lucky to happen to be located close to the carbon source. But they can also swim, the bacteria, so they can also look for the carbon source themselves.
Yes, I don't have any questions, just to see if there are any questions in the chat. So I'll give maybe Sarah, if you have any questions.
No, I don't have any questions on my side. It was a really interesting talk. I learned very much about microbiological induced processes. So thank you for this. And we have a comment from Chiara. We also thank you for the great talk.
Thank you, Chiara.
So if you don't have any more questions, I think we can finish here. So thanks again to our speakers and to the audience. And I would like to say that if you are looking at the webinar afterwards, do not hesitate to contact the speakers or to let comments on YouTube. I guess I would be happy to see them afterwards. And finally, I would like to advertise our next session, scheduled on the 13th of January at 3:30 Central European Time. And our speakers will be Silvia De Simone from the Institute of Environmental Assessment and Water Research in Barcelona, in Spain, and Aurelia Bucciarelli from the University of Bern in Switzerland. And so this session was organized by her, as a member of the Pore Media Time Talk team. So if you have any feedbacks, want to be involved as future speakers, or just subscribe to our mailing list, please feel free. The mailing email address is here. And so thanks again for joining us today. Stay tuned for the next Pore Media Time Talk, and enjoy the Christmas and New Year celebrations, and see you next year.
Yes. Bye everyone, and Merry Christmas and Happy New Year to everyone. Yes, thank you. Bye.